Okay, so then this is part 5. Okay, so, well, Rafael, thanks for the invitation, and also Carlos. It's always a pleasure to be in Mexico. As you can see from my title, I'm going to talk a little bit about dispersive estimates for Schrödinger equations. Maybe let me start by setting the stage. What is, of course, the final goal in some sense is you want to understand nonlinear PDEs. Okay, something like nonlinear Schrödinger equation. You want to prove something about maybe stability of solitone solutions for these equations. And for this, you need a couple of things as an input, and dispersive estimates are one of the basic things which we are going to need there. So I'm going to mainly focus on these things in this course, and at the end then say a little bit about how you apply this whole thing. Okay, so and also before starting, I'm going, well, first I should mention you will not see many PDEs because we're going to look at discrete models because things are a little bit simpler and it's easier to explain some of the main ideas without going into all the technicalities. Also, I will try to prove most of the things I'm saying. Well, I will not always be able to be giving complete proofs, but at least giving you some of the main ideas, what is behind it. And also I'm going to very slowly. So we're first going to recall some things from ordinary differential equations to set the stage and to put everything into perspective. And in some sense, the results I'm going to tell you on later on a little bit is about one-dimensional discrete Schrödinger equations. If you want to know more about this, you can look, for example, in this paper here. I'm also going to talk a little bit about semigroups, and there are two classical references here. And as I said, I'm going to start out with ordinary differential equation, and also there's one possible reference here. Okay, so let me begin with something very basic. All of you definitely know this. So we look at an autonomous system, linear first-order differential equation with constant coefficient. We look at the corresponding initial value problem. So the initial value at time 0 is given, and A is just our coefficient matrix, so and just constant n by n matrix. And we also know it's easy to write down the corresponding solution for this system. It's just given by the exponential matrix of TA applied to the initial vector. And of course, the exponential of a matrix is defined like the exponential of a function using the corresponding power series. And it's a very simple exercise, of course, to verify that this converges by just comparing with the classical exponential function, and then you easily see you get a convergent power series, and this way you can write down the corresponding solution. You can also easily prove it exists. We are more interested in the fact about or asking ourselves what happens when you wait for a long time. So is the solution stable? Meaning does the solution remain bounded, or is it even asymptotically stable, meaning does it go to 0 as t goes to infinity? And here, of course, is where spectral theory comes into play. We answer this question by looking at the spectrum of the corresponding matrix. In this case, it's a matrix. It just has eigenvalues, and all we need to do is we need to look at the real part of the eigenvalues. If all real parts are negative, then we know it is asymptotically stable. Everything goes to 0. If some of the real parts have 0, then things are a little bit more tricky because it depends on whether you can diagonalize at least this part of the matrix or not. If you can, then you are stable. Otherwise, you have some polynomial terms. And let me also recall briefly how you prove this. Well, in the case of matrices, you have this Schrödinger canonical form in which you can bring the matrix, and then you can easily compute this exponential matrix, because the definition we had, of course, in general, it's hard to compute this series, but you can do it once you transform your matrix to a simpler form. And the simplest form in this situation is this block structure, where each block is of this form. You have the eigenvalue on the diagonal, and you have this nilpotent part on the on the second diagonal. And once you have this structure, you easily can compute the exponential. It just is the exponential of the individual blocks, And for one block, it's also very easy. You factor out this term here, so you get e to alpha times the eigenvalue, and then the nilpotent part will eventually stop after a finite number of steps, and so you get this matrix right here. And then, of course, you know, in order to understand this exponential thing here, you split it using Euler formula. So you have e to the real part of alpha times t plus sinus plus I cosine S. The only interesting part from the long-time behavior point of view is this part here, and if this goes exponentially to 0, then the whole block will go to 0 because the polynomial terms will not interfere. And if it is 0, then this thing here will be bounded, and the whole solution will be bounded if you don't have these polynomial parts here, so you can diagonalize the corresponding part. Okay, so this should be well known from your ODE course. And you can try to apply the same kind of ideas, of course, to partial differential equations. You can look at your partial differential equation as such an evolution equation right here, writing it formally in this way. I have done this for simplicity for the heat equation. And in this case, the matrix now is an operator. It's the Laplace operator. Formally, it looks the same, but of course the big problem now is that the Laplace operator is unbounded, right? So it's not so clear how to define the exponential function, even though this can of course be done. But then you need to look at corresponding Banach or Hilbert spaces where you can define this properly, and things get much, much more complicated. Of course, if you're in a little simpler situation, if you're, for example, in a discrete model, then you don't have differential operators, but you have shift operators, which you already have seen in the talk by Hermann in the morning. And these shift operators have the big advantage that they are bounded, so you can still do the same thing and just define your exponential of an operator using a convergent power series. And you have this, which is then called operator group. If everything is bounded, it's a group. In case of Laplace operator, you only get a semigroup, but we come to this a little bit later on. Okay, but at least in the simple situation, you can play the same thing and then investigate this corresponding group or semigroup. But still, let me mention that the semigroup issue here is very important, as you know from your basic PD course. If you look at the heat equation, your fundamental solution is this Gaussian, and if you go into negative time directions, eventually your Gaussian will develop in this Dirac singularity, and you cannot go any further backward. And this shows you that the time evolution goes only into one direction. So in general, for an unbounded operator, you can only expect to have a semigroup, but you cannot expect to have a group in such a situation. Okay. But let me then still continue with this a little bit. So in this situation, one looks at this abstract Cauchy problem where X is now some Banach space and A is an operator in this Banach space. And if you look at this equation, you expect that the solution, again, can be written in such a form because the equation is linear. The corresponding solution should also depend linearly on the initial condition. So it should be some solution operator applied to the corresponding initial condition. And then you just go or take everything on from backwards. You just define what you would like to have from your solution operator. So you define that it should have the following properties. So it should be only defined for positive times, as I just argued. For PDEs, that's the best you can do. And you want to have some continuity properties. Of course, your first guess would be to assume that this is just continuous when you look at it as a map from the reals to the bounded operators. But this is a little bit too much to ask for, so you can play a little bit with this, and then you will see it will be continuous if and only if the corresponding operator here is a bounded operator, but the Laplace operator is not bounded, so you rule out this if you ask for this. So the next best thing you can go for is replace continuity in the operator, in the norm topology, by strong continuity. That means requiring that for a fixed x here, this is a continuous function from the reals to your corresponding Banach space, so from the positive reals to your Banach space. So this is the strong continuity property. And then you also have the semigroup property. So at 0, of course, it should be the identity. It should give you back your initial value. And if you go from 0 to times t plus s, it should be the same as first going from 0 to s and then going from s to t. So you should have this semigroup property right here, which is in some sense just rephrasing that the corresponding solution should be unique. Okay. And in this context, the operator A is called as the infinitesimal generator of this semigroup, and the name somehow is explained by this formula right here. So if you look, this should be the solution of this equation here. So that means if you differentiate this formula, you should get your A back. And if you just differentiate at 0, then you get your operator back from the corresponding semigroup, and hence in this sense it just generates your semigroup via this formula right here. Okay, and if you write down this limit, then of course you should worry about existence of this limit, but at this point one cannot answer the question and just says, okay, this is not an operator which is a priori defined on the entire space. It will be defined on some domain, and the domain are precisely those x for which this limit here exists. Even though at this point it could be just a 0 vector. It might be not more, even though, of course, always for nice theory this does not happen. Okay, we are going to make an extra assumption which is not necessary but simplifies life a little bit and is fulfilled in many applications, in particular in the applications we have in mind. So we're going to assume that we have a contraction semigroup, meaning that the norm of these operators here is smaller or equal to 1. So things don't grow, they remain bounded. And in this case, one can give a characterization of those operators which will give you a corresponding strongly continuous semigroup. So that means now if you have your heat equation, what you need to do is you need to take your Laplace operator and you need to try to check these conditions right here. If they are satisfied, then you get a corresponding semigroup for your solution. And the classical theorem is this Hill-Yoshida theorem. So a linear operator, and important, unbounded is of course included here, is the infinitesimal generator of a contraction semigroup if and only if it's densely defined, it's a closed operator, meaning that the corresponding graph is closed. Should I say something about how this is defined, or? Okay, here we go. So if we look at the graph of our operator, then this is just the set of all pairs, so just graph in the usual sense for x in the domain of our operator, and this is of course a subset of x times x, and this just should be a closed set. Okay, so very simple definition. What this boils down to is the following thing. We all know that operator is bounded if and only if it is continuous. Okay, Laplace operator is not continuous, and the second best thing you can have is this boundedness here. And if you work it out, what does it really mean? It means if you have a sequence of values here which converge, so the xn converges to some x and the axn converges to some value y. If this happens, this should be ax. Okay? So that means in some sense you can have two things. If you plug in a converging sequence into your operator, if it's bounded, you get convergence of the image sequence for free. If it's not bounded, two things could happen. It could not converge at all, or it could converge, and closed operator says if it converges to the right thing. Okay, so in some sense, that's a replacement of continuity, the second best thing you can have for unbounded operators. Okay, so that's densely defined closed operator, and the important thing is this resolvent estimate here. So if you look at the inverse operator at the resolvent, then first of all, that should exist on the positive half line. So for values lambda larger than 0, the resolvent should exist as a bounded operator. So that means you are surjective and injective, and the norm should be smaller than 1 over lambda. Okay? And precisely if these conditions are satisfied, you get a corresponding semigroup of contractions satisfying this estimate right here. Okay, and yeah, so I don't want to prove this theorem here because it would lead us a little bit too far, but this is one of the classical theorems, and it's also not very difficult to prove. Do I miss a slide? No. Okay, and of course we have seen this resolvent estimate here, but still if you have an operator and you try to verify this, you see you would as first thing need the resolvent. And resolvent really means you need to invert your operator, and for a given operator that's not completely trivial, right? I mean, even if you think about the Laplace operator, okay, for the free one without any potential or something like this, you can explicitly write it down. But as soon as you add a potential, you do not have explicit expressions anymore. So this might indeed be very hard to check. And there's an easier way, which eventually boils down to being equivalent to what we have before. But this is this Lummer-Phillips theorem, this equivalent formulation. And this tells you that you can also check the following two conditions. So the first one is the same as before, but now instead of the resolvent estimate, we have this dissipative estimate here. So we look at the scalar product xax, and the real part should be not smaller than 0 for every x in the domain of our operator. And you have, if you have this estimate right here, then again it will generate a contraction semigroup. So we will need a little bit in order to verify equivalence. It doesn't take long. You will need the trick. Maybe if you try it yourself, you will fail. But if you look it up, you see it's not so difficult. Let me still motivate this condition right here. So if x of t is your solution, okay, and we said it should not grow. If it should not grow, and we take the derivative with respect to time, then this should be non-positive, right? In order for this not to grow. We say we are in a Hilbert space, so of course this is the reason why I put the square here. I can express the norm like this. Oops, I forgot my differentiation. And I then just differentiate this whole thing, and what I get is this expression right here. Okay? So the derivative will be just 2 times the real part because of symmetry of the scalar product of x dot. X satisfies our differential equation, so we replace x dot by ax, and then we get this thing right here. And we want this if this expression shouldn't grow here. And t or t is equal to 0, of course, makes no difference by shifting everything. And hence we see that we are led to this condition here, and it's maybe now no longer so surprising that you also can go in to the other way. Okay, I have formulated this theorem here for Hilbert spaces, whereas I had Banach spaces in the previous example. Same thing works in Banach spaces, but it's a little bit more elaborate to formulate this condition right here without a scalar product. So let's just forget about this and continue. And one more thing, of course, well, let's also worry for a second. What has this, or how does this fit in with the matrices we have started with? Okay, what does it mean, the condition before? What does this condition here mean? If you plug in an eigenvalue, of course, this tells you then this will be just the real part of your eigenvalue. you get back the same condition you had before. Okay, so that really shows you that the spectrum of your operator should be in the correct half plane as before. Okay, so you get back your result for matrices from this as well. Okay, yeah. Okay, so yeah, I will now mention that I don't want to say much more about this at this point, because we are going to look at most of the time Schrödinger equations without a potential, where we can even explicitly compute this operator here, and so I'm not going to pursue this at this point. Okay, now let me go a little bit back to ODEs and motivate what is done for PDEs by just looking at this simpler situation right here. Of course, in many situations you look at linear problems, but you have some nonlinear problem in mind, and in some sense the linear one is the simple first order approximation to your problem, and for the real problem, for the nonlinear, you can write it in such a way. So again, you have your differential equation, here's the linear part, plus there is some nonlinear part which you want to regard as a perturbation. Okay, so you consider this to be a small perturbation of the original thing, and somehow what you want to do is you want to use information you know already about this linear equation in order to find something out about this nonlinear equation right here, and it's precisely what we are going to do next. And in particular, first simplest question would be, if you know that the linear system is asymptotically stable, is the same true for the perturbed system, or more precisely, under which conditions on the perturbation does this remain true? Okay, so let's move on to the next thing. And let me recall this classical theorem for differential equations. So assume that A is asymptotically stable. And this means, if you look again at your Jordan structure, that you have an estimate like this. All of these blocks here can be estimated by an expression of the form a constant times t to the alpha t. If you don't have any, if everything is diagonalizable, then you just can take the minimum over the real parts over the eigenvalues right here. Otherwise, if you have polynomial terms, then you just need to shift this here by an epsilon. But in any case, you will have an estimate right this for all the entries of your matrix, and hence also for the corresponding matrix norm. So this norm here is just the standard matrix norm for, or the operator norm if you want so, for some constants. Okay, and what are we going to assume about our perturbation? Well, we're going to assume, of course, that at x is equal to 0, so for a small initial condition, it's going to vanish, and it should be at least vanish linearly. Okay, so you have some constant g0 times the norm of x. So let me emphasize, I don't emphasize this on my slides, but it's a system. And if I just use these single bars here, it's just the Euclidean norm of the corresponding vector. So let's assume we have this in a neighborhood of 0, so some small delta ball around 0, and for positive times. Then if you have this condition here between the constants, so if this constant in the estimate here times this constant here is smaller than alpha, then you again get a solution which goes to 0 exponentially fast, and you can even write down an explicit estimate right here. And from this explicit estimate, of course, you also see where this condition is coming from. You want this quantity here to be negative in order to make sure that everything goes to 0. And of course, it's a local result, so everything holds in a small vicinity, so it holds in a ball of radius delta over c, and everything is only true for positive times. Okay, so let me sketch how you go about proving this. So the first trick you do is you take your solution and then you multiply with e to the alpha t, because then you know you get something bounded. Okay, so you switch to something new, to this y of t here, which is given by this expression and which now has the advantage by your assumption on the linear system that this here will be bounded, at least for the linear system. Without perturbation, this would give you something bounded. Okay, and let me just, I'm wondering, I think I'm missing something. Yeah, I'm missing something here in my proof. Okay, we're going to make the transformation in a second. First of all, now here comes the first important ingredient, which you also use. You use precisely the same ideas for nonlinear PDEs. You rewrite everything using this Duhamel formula. Okay? So you use that if you have your linear equation and you have the corresponding inhomogeneous equation, then you can write down the solution of the inhomogeneous equation as the linear part of the solution plus this particular solution of the inhomogeneous solution, which is just given by this expression here. Okay? If you formally apply this to your perturbed equation, then of course you don't get a solution formula, but you get an integral equation for your solution. So you get this integral equation for your solution, and then you're trying to solve this integral equation using iterations. Okay, so you're applying Banach fixed point theorem to this thing here. Here we don't need to apply Banach fixed point because we already know from standard ODE theory that there is a solution and we're only interested in the estimate. How do we get the estimate? Well, it's a standard Cronval type thing. So we look at this integral equation and we're trying to estimate everything. So we take absolute values, we take triangle inequality, and then we estimate this here by the corresponding operator norm. We just plug in the estimate we have assumed for our system, and then we get this estimate here for the norms. And of course, be aware that this is only valid as long as the estimate for our perturbation is valid, so only in our delta ball, right here. Okay, so now we make this little transformation. Then we can write it like this. So the e to the alpha t will somehow go away. We apply Cronval to this thing right here, and Cronval tells us that we have this estimate. We undo our transformation, and then we precisely get this estimate I have shown you before. And so we see that if everything stays close enough to 0, everything is nice, and we have this stability result that at least in this neighborhood the perturbed system is again stable and even exponentially stable, so solutions go exponentially fast to 0. Okay, so let me discuss this, or let me emphasize a few things again. So the linear part in somehow captures the important thing. It's not going to be destroyed by the nonlinear part, at least if the nonlinear part is sufficiently small. So for example, okay. Yeah, and for example, if we assume that this function g has no linear component because we put everything into the linear matrix A, then of course that would mean that the first derivative of this function g here vanishes at 0, and that means there's no linear part, and we can make this g0 as small as we want as long as we make the neighborhood sufficiently small. So that means that shows that asymptotic stability persists under nonlinear perturbation in a small neighborhood. And again, let me re-emphasize, the important thing was using this Duhamel formula, rewriting everything as an integral equation, and then estimating and playing with this integral equation. And the second ingredient in this proof was a good qualitative understanding of the linear part. Okay, so it was not good enough to just know that the linear part has a solution and maybe has continuous dependence, like you have when you know you have a semigroup, but we needed more. We needed an explicit estimate on the decay of the solutions. Okay, so this again shows you how important it is to understand the linear part of the equation in order to be able to say something about the non-linear part. Okay, so that means if we want to generalize something like this, we really need a good understanding of the linear part. Whenever you have something like this, you can generalize this idea. So for example, here you could generalize this if you have a periodic equation, then you have this Floquet theory, and you have a similar estimate, and you get the same result. Okay, but if we want to do the same thing for PDE, if we want to generalize this to strongly continuous semigroups, then of course things get a little bit more tricky. I don't want to go into full details here because we are looking at discrete problems later on, but let me still point out a few things which are problematic. Okay, so we have formally the same system. Again, we can do the same thing, write down Duhamel's formula, at least formally, and just verify that it solves our differential equation. But if we try to verify this, we run into one problem. The problem is differentiating this integral right here. Okay? Because we can only differentiate when we are in the domain of our operator, so we see that even though this integral here makes perfect sense for a nice G, let's say for a continuous function, so that we can define it just as a Riemann sum. Of course, we have to be careful. We are in a Banach space now, so we have to worry a little bit how this integral is defined. But if it's a continuous function, write down the corresponding Riemann sum, and everything is okay. But continuity is not enough to make this differentiable. Here you would need, for example, that G is in the domain of your operator, so the image of G is in the domain of your operator. Then you get a corresponding solution. This already shows you that things can be tricky. So, for example, people then would say that this formula here gives you the mild solution, and if you can verify that it's actually differentiable, then it would be the classical solution, even though classical doesn't really mean that it is sufficiently differentiable in the end. Okay, so there are some problems, but I don't want to worry about these things at this point. Just point out that you have to be careful. Okay, now the next thing is, once you have a solution, how do you get this stability estimate? How do you get something like this? How do you verify exponential stability? Of course, your first hope would be that an estimate on the spectrum is good enough, but again, in the infinite dimensional setting, this is not good enough. There are a couple of results. One of the well-known ones is this Gerhard-Pruss-Greiner theorem. We are in a Hilbert space. We have a strongly continuous semigroup, and this is uniformly exponentially stable if and only if the resolvent set of the generator contains the half-plane. So this is the spectral condition you would expect. Plus, it satisfies this additional resolvent estimate right here. In some sense, this tells you that when you go with the real part to 0, everything should be bounded and is not allowed to blow up. Okay? This is, of course, true if you look at the matrix case, because you have some eigenvalues, but they don't go up to real part 0. They don't go up to the imaginary line. And that means you don't have any blow up when you go in this direction here. But in the infinite dimensional case, you not only have eigenvalues, you have continuous spectrum. So even though you stay away locally there, still you need to make sure that you don't have any blow up. Right here. Okay. And let me also mention one more thing. If we look at the conservative case, and conservative now would really mean that the real part of the eigenvalues are 0. So things don't go to 0. You're just looking at stability, and now that asymptotical is stability, then you have to realize that the situation is much, much more tricky because this is unstable under perturbations. Okay? And just look at this similar, this simple ODE on the real line. You just have x dot is equal to x squared. You can easily write down the solution, and you see you have blow up in finite time. So you see, even though the linear part here would be 0, so the linear solutions would be just constant, so no blow up as soon as you add a small perturbation. And of course, you could add an epsilon here. It will not change anything. You will get blow up. So stability is typically not preserved. Okay, but still, you can do something, and let's look a little bit at the ODE case. So let's just suppose that your matrix A is stable. So you have an estimate of this thing. Your unperturbed solution remains bounded. And suppose that you have this estimate right here. So very similar as before, but now I don't want a constant here, but something depending on time. Okay? And the important thing is, what I'm claiming now, if this function here is integrable, then stability is preserved. Okay? And this is what I want to emphasize with this theorem here, that now you need some integrability, you need some decay, otherwise you will not get stability of your problem. Okay, so we are assuming that this thing here is integrable, and then I'm claiming again the solution of the perturbed system is stable, at least if you start in a sufficiently small neighborhood of 0. And the proof is pretty much the same as we had before. We start with writing everything as an integral equation. We estimate everything just plugging in our corresponding estimates for the linear system and for the perturbation. And now you already see you want again to apply Kronwall's estimate, and you get the integral over this g0 of s. If it's a constant, it's e to the g0 times s, which blows up. But you get this integral here. If you assume that this integral is finite, you just can replace it by taking the integral up to 0, and you get that your solutions remain bounded. Okay, so observe that in this case, that's the important thing, you do not get anything from the decay of the solutions for your linear equation, but we needed to assume that the decay comes from our perturbation for our result to work. And actually for ODE, this is the end of the story, but for PDE it is not. And the reason is the following. If you're in a finite dimensional space, of course you know from your basic functional analysis course that all norms are equivalent, right? And in infinite dimension, that's no longer true. And that means if you have this linear equation and look at it in a certain space A, which means taking a certain norm, you might have bounded solutions. But if you take a different norm, you might have decaying solutions. So that means even if you have a certain natural setting for your solution, let's say some Hilbert space, and you have a system which preserves the norm, for example, Schrödinger equation preserves the norm during the time evolution, so you have no decay whatsoever. Once you change your norm, you might get decay. And this is, in the end, we will see this, what dispersive estimates are about. So if you don't look at the time evolution in your original Hilbert space, which maybe was the natural one from a quantum mechanical point of view, but change your norms, you might get decay from your linear equation. So you have one more thing you can play with. You can play with the norm. And if you get sufficient decay such that things are integrable, you might be able to prove stability. Okay, so let me try now to explain what I mean here, and let's look again at the heat equation. Okay, so you know from your basic BDE course that we have this fundamental solution, and if we take the convolution with the fundamental solution, it will be the corresponding solution of the heat equation. So we have this very explicit formula right here. Okay, and for example, you could estimate this here. Let's assume we have, it's really heat equation, we have some heat distribution or some mass. Things are positive, and then of course you just can compute the L1 norm of this thing here. You use Fubini in order to interchange the order of integration. You just get the integral of g. Then you have the integral over your Gaussian, which is normalized to 1. So you see that the L1 norm is preserved under this evolution. So nothing is lost, no mass is lost, no decay, but the norm stays the same. On the other hand, if you assume that this g, for example, is integrable, And you don't ask what is the L1 norm of the result, but you ask what is the L infinity norm of the result. Then we can estimate the same thing here differently by, again, taking absolute values, but now taking absolute value of this exponential here, which is just 1. You again get the L1 norm of G, but you still have this term here, so you see you get time decay. Okay? So you see that the infinity norm decays like 1 over t to the n1 half, and this is this typical dispersive decay which you have in n dimensions. Okay, and you could even combine these estimates and then interpolate and get some corresponding estimates for the p norms in between, but at the moment this is good enough for us. And please, of course, observe we do not get exponential decay out of this, but we just have some polynomial or 1 over polynomial type decay. And depending on the dimension, this might be integrable or not. Okay, in 1 dimension, we have 1 over the square root, which is not integrable. 2 dimension, 1 over t, still not integrable. 3 dimensions would be okay. But you can get even stronger decay if you take weighted norms, but we will come to this a little bit later. Okay, so let me draw some conclusions from this. First thing is you can treat nonlinear equations as perturbations using this Duhamel formula. Okay, so that's the main ingredient. That's usually the starting point. If you want to do this, you need a good qualitative understanding of the underlying linear problem, plus you need some good estimates for this linear problem. And if you're looking at dissipative systems where you have exponential decay of the linear part, things are fine. This carries over to at least sufficiently small perturbations. But if you have a conservative system, so where you have no decay of the solutions, you still can get some polynomial decay if you choose the right norms in your infinite dimensional space. Okay? So these are the things I want you to remember. Okay, so let's look at Schrödinger equations and let's try to further explain some of these ideas. As I said, I want to keep the technical problems at a minimum, so I'm looking at the discrete Schrödinger equation, and for the moment now I'm looking at the free Schrödinger equation where there is no potential, so I just have a shift to the left plus a shift to the right plus this diagonal part, even though this is just a shift of the anti-operator, so you could even do away with this one, but if you write it like this, it looks more like the discrete Laplacian in 1 dimension. Okay, and I mentioned before, this would be the corresponding abstract Schrödinger equation here. You can easily write down the solution because this H0 is a bounded operator by just writing down the corresponding exponential function. This will converge nicely, and you can even check that this is a corresponding unitary operator because H0 is self-adjoint and e to the I something self-adjoint. It's basically Stone's theorem, even though in this bounded case you don't even need Stone's theorem in order to understand this. You have a nice unitary time evolution right here, and in particular that means that your L2, little L2 norm of the solution is preserved. So no decay for the L2 norm. Hence we need to look at some other norms. One natural thing is, of course, looking at LP norms, and the simplest thing would be, as I mentioned before, taking little L1, little L infinity, but the problem, we just will get 1 over square root of t decay, and as I have pointed out, 1 over square root of t is not integrable, so this is not good enough. Okay? So hence one adds some weights here, and you just, let me write this down. It looks maybe a little bit more confusing than it is. So let's say, for example, you say sum over, I'm n in C now. So this would be your L1 norm. And then I can add an additional weight by putting it in like here. And I can play with the powers here, and this is basically what I'm doing in this norm. So P is just the usual LP norm, and sigma here just stands for the weight. So this would be sigma is equal to 2 for the L1 norm, and that just means that you require additional decay, right? The higher this power here is, the stronger the corresponding sequence has to decay near infinity. And if sigma is equal to 0, this weight is gone, and this would be just your classical space without any weight. Okay, so these are the function spaces I'm going to work with, so please remember this definition right here, but it's just this weighted space. Okay, so now let me explain what I mean by dispersion. So typically, if you ask physicists, they will tell you, well, dispersion in a linear equation means you have a linear equation, you have plane waves, you make your ansatz, this plane wave right here, plug it into the equation, and then you get a relation between these two parameters, theta and omega. Okay, these are just your two unknowns in your constant, and it will satisfy your equation if and only if they satisfy this relation right here, which physicists would call the dispersion relation. And that tells you that different plane waves travel at different speeds. Okay, so the speed of this wave is related to the wavelength. If they would all be the same, which happens if you just look at the wave equation, all of these plane waves would travel at the same speed, independent of the wavelength. But in this case here, they will travel with different speed. And so when you look at the superpositions of these wave packets, this will lead to destructive interference, and hence these wave packages will decay. At least this is what a physicist would explain to you, because if you write down, let's say, two sine equations with sine omega 1, sine omega 2, and add them, and the two frequencies don't add up, then you will see that you will get some decay, because some positive part will be added to some negative part, and there will be some cancellations. So the mathematical way of understanding this is using, okay, I'm going to come to this in a second, is using oscillatory integrals. And you see this by, of course, first noting that you can write down the solution in the following way. Okay, so first of all, what is a wave package? You just say we have these plane waves, which we had before. We have a linear equation, so we can take linear combinations of them. And of course, you can take continuous linear combinations, so you can take an integral, and you can write down a solution of this equation like this right here. So you take this coefficient c in front of your plane wave to be dependent on the wavelength, and then you just integrate, and making some assumptions that this integral exists here, and so that you can interchange differentiation and integration, you see that you get a corresponding solution right here. Okay, and moreover, of course, this function here, these coefficients are basically just a Fourier transform of your initial condition. So you see that basically any solution of the initial problem can be written like this. So the C of theta is just the corresponding Fourier transform up to this 1 over 2 pi right here. Okay, so you have this formula, and I'm wondering, I'm looking for something. Okay. And putting everything together, we can write down the solution like this. So as I said, one way of writing it would be the exponential function, and the other way of writing it would be just this formula we got by Fourier analysis, if you want to, by writing this together. And moreover, we can, by just inserting this expression here, write this as an integral with a kernel. Yeah. And you can formally write it like this, interchanging summation and integration, by finding that this operator here is given by a summation operator with this corresponding kernel right here. Okay?
Where the absolute value come
The absolute value comes from because you have a symmetry here. The sign doesn't play a role. Okay, but you can also remove the absolute value. It makes no difference. You don't see it if you just start from this formula. You do not have an absolute value. Okay, but there's a symmetry, and you can look at this integral and see that it does not depend on this sign, and hence you can put an absolute value in here. But you need to make a change of variables in this integral in order to see this.
That's very particular to Laplace operator.
It's very particular to the Laplace operator that it depends only on the absolute value of the difference. So it's a symmetry of your problem which you see here. But you're right, it may be good to point this out. If you just take the formula from before and plug it in, you do not have this absolute value here. Okay, but the point is we can write it as such an integral operator, such a summation operator with this integral kernel here. Now, this integral can be evaluated in terms of Bessel functions. So if you plug this into Mathematica, or if you go to your favorite series of tables of integrals, you will find it can be written in terms of Bessel functions, and it has this explicit expression. But for our purpose, we do not want to use this explicit expression, but we want to see how to get this decay directly from this integral, because it's something which only works for very simple problems where you have an explicit solution. As soon as I would add a potential, this is no longer going to work because I don't have an explicit solution. So for me, it's going to be important to understand how the decay comes from the integral. Okay? So let's try to do this. And maybe let's still look once more at this integral here. Of course, now if you look at the t dependence, here's the t. Okay? As t increases, we have this expression here. It's e to the t, something which is definitely real. So that means it's sine and cosine, and t is the frequency. Okay? And it will oscillate faster and faster as t increases. So it's clear that there should be some cancellation in this integral here. And in some sense, you could also see it as Riemann-Lebesgue lemma for this integral right here. You get some cancellation. But of course, we want more. We do not only want to argue that it goes to 0. We want to have some explicit estimate on how fast this goes to 0. But that's the main idea here. You have an oscillatory integral. As t goes to infinity, it oscillates more and more. So you expect that there should be more and more cancellations. So things should go to 0. And so the question is now how.
Theta is 0. Except if theta is...
We will come to all these little details right here, of course. There will be problems. Okay. But anyway, there's, of course, this classical method, which I want to discuss next, of stationary phase, which will tell you that the main contributions will come from the stationary phase points, and you can investigate all this. But the first thing which we are going to do is, if we want to look at the asymptotics, we have, well, it's not really a plane. In the continuous case, it would be a plane. In our case, let's say here is n, and here is t. Of course, n is just discrete. But anyway, we're going to do the asymptotics in the following way. We're going to fix a certain velocity here. Okay? So we're going to fix this v, which is the lattice integer, which is just the n over k, which we had over t. So in some sense, we just fix a certain velocity, and we're going to look at the problem in this direction here. Okay? So we are fixing v, we're taking this constant, and then we are investigating the asymptotics. So that means in some sense when you look at your wave, you don't stand still there, but you're moving into a moving frame. You're moving with speed v, and you look how things evolve when you follow the wave with this speed v. Right here. But in some sense, that's no restriction, because in the end, you will get something which will be estimates which will be uniform in v, so you get something for your original thing. Okay. So one important thing, as I said, in the end it needs to be uniform, but temporarily we're going to use these new parameters t and v, and one thinks of v as the slow variable, which is not going to change, which we are going to keep essentially fixed, and t is the fast variable. This is the one we send to infinity, but in the end we would like some estimates which are independent of v, at least in some sectors. It depends on the problem what you can get here. Okay, and we want to have a quantitative estimate, because in most situations when you look at the stationary phase method, you will write down some explicit asymptotics for this integral, but the explicit asymptotics will only work in a certain direction, and as I said, we want to cover all directions. We want to have something uniform, and the nice estimate for this is known as van der Corput lemma.
If you take the velocity, I mean the speed to infinity,
yeah.
do we have a semi-classical limit? So when
For this v here, I would need to think about it, but I don't think letting v goes to infinity gives you anything interesting here. And I would not really call this a semi-classical limit in this context. It's really, these are the different velocities you can look at, but the point is there will be some interesting directions where interesting things happen, and there will be some directions where not so interesting things are happening. So typically there would be some sector where your stationary phase points are, where you can write down some interesting asymptotics, and there will be other sectors where things will decay very fast. Okay? And in particular, I would need to check this, but my impression here is that if v goes to infinity, then things should be decaying very fast, and it's not an interesting regime. But as I said, for me the important thing, I want to have something which is uniform, which works everywhere. So I need a good estimate which is not depending on v. I don't want precise estimates for fixed v. I want a good estimate which works for all v. This is my game right here. Okay, so next thing I want to discuss this van der Corput lemma, and I want to discuss this in a general situation. So we have an integral, oscillatory integral of this form, integral over some interval from a to b. We have some coefficient function a of theta, some term e to the et, and some function phi here. Phi is called the phase, a would be the amplitude of this problem here, and I want to know what happens as t goes to infinity. Riemann-Lebesgue tells us this should go to 0 if a is a continuous function, but we want more to get out of this. And of course, maybe also remind you that if you do integration by parts, then of course, depending on how many times you can differentiate here, you just get 1 over t squared, and so on, except when phi is equal to 0, right? Because when you do integration by parts, you get a 1 over phi of theta. So if this vanishes, then you have a problem at these points. And these are precisely the stationary phase points, okay? Precisely where the derivative of v vanishes, where you don't have something linear. Okay, so let's look at this lemma right here. So I'm looking at this integral, and by the way, a and b could be minus infinity and plus infinity. It's not important that this interval is bounded, even though in our situation it is bounded, which is related to the fact that we have a bounded operator. The absolutely continuous spectrum is bounded. This is what you see here. If I would look at the discrete Schrödinger, the continuous Schrödinger equation, this would be from minus infinity to plus infinity, but this is not important for this lemma here. A and b could be arbitrary. Okay, so I'm looking at this situation. I'm assuming that phi is a nice function, differentiable. If we look at our example, typically this will be analytic, okay? So this will not be an issue. The amplitude is coming from the Fourier coefficients. So here I don't want to assume too much, but we will see we don't need this. And in fact, as we will see, the important thing is to look at the case when the amplitude is not here, when it's equal to 1. That will be sufficient. Okay, so we look at this integral here where there is no amplitude, where amplitude is equal to 1. We are assuming that this has a number of derivatives, L derivatives, and we want these derivatives to be bounded away from 1. Okay? 1 is not important here. It could be epsilon. You can always scale it to this situation. And in addition, if L is equal to 1, we also need that the derivative is monotonic. But it's somehow clear from this condition here. I mean, it cannot be 0. So if we assume it to be continuous, it cannot change sign. Okay, and the claim is there is some universal constant, C of L, difficult to determine, but anyway, there is some, the optimal value, there is some constant such that this is the case like 1 over T to the 1 over L. Okay, this is this van der Corput estimate. And let me emphasize, if you want to apply this, you would do the following thing. First, you compute the derivative, and then you hope if your derivative doesn't vanish, if it's larger than epsilon, then you're all good, and you can apply this. It will go to 0 like 1 over t. If the first derivative vanishes somewhere, okay, you take the second derivative, and then you hope that the second derivative doesn't vanish. Again, if it doesn't vanish, good. Otherwise, take one more derivative. Plus, you can also do an additional thing. You can split your integral. So if there's one point where the first derivative vanishes and another point where the second derivative vanishes, if this doesn't happen at the same time, at the same points, you can split into intervals and apply it on different intervals. But that's basically the approach. You compute the derivatives and try to find something which is non-vanishing. Okay, and as I said, epsilon is good enough. I called it delta here, sorry, and epsilon on the blackboard. If this is larger than delta, then just rescale, and then the result looks like this. So without loss of generality, we just prove it for the case where delta is equal to 1. Okay, so let's call this integral I of t, and we are going to use induction. We start with the first case where L is equal to 1. L is equal to 1 is simple because we are just using integration by parts. Okay, so we take I of t, we make one integration by parts, then we write it like this as the formal derivative here. This is, of course, the inner part. You already have the 1 over t term here. You make integration by parts, and you get this value right here. And now you just estimate everything. You take absolute values. These are the two boundary terms. This is this integral right here. You plug in your estimate for phi prime. We know that this is always larger than 1. So 1 over phi prime is smaller than 1. And then we get this estimate right here. So we get, I think I see. It's even better to not estimate it like this, but just to do the entire integral and estimate this thing like this. And then you get that this is smaller than 2, because now we have the, now we have the estimate that 1 over phi prime is smaller than 1. Okay, so we get the case L is equal to 1 with C1 is equal to 2. And it might well be that for L is equal to 1, 2 is the optimal constant. But then as we go on, it's difficult to see what the optimal constant is. Okay, now let's try to continue, and let's try to make the induction step. So let's suppose that the L plus 1th derivative is larger than 1, and we already have proven the L case. So then there can be at most one point such that this Lth derivative vanishes. Why? Don't fall asleep. You have some, you know that it grows with a growth rate of at least 1, the Lth but 1 derivative. So if you integrate, there can be at most 1, 0, right here. Okay? And we get that the absolute value here is larger than delta if we take a small interval around this 0, right here. Okay, then we know outside this interval, so here is minus delta and here is plus delta, we must be larger than delta, and we can play this trick I mentioned before. I split everything. So I split it into an interval here, an interval here, and then a small interval in the middle. The interval here and here is covered by the case L, which we know, which is our induction hypothesis. Okay, so we split it into these two pieces, and the one piece from the outside part we can easily cover. Now let's look at the inner piece. Okay, so this is from the induction hypothesis. And now for the inner piece, we choose delta like this. Okay, so we make this special choice, and this choice is made in such a way that we just balance the two contributions from these two parts. And if you plug this in, then you see that you get your corresponding estimate with this constant CL depending on the previous constant, and you get this recursion right here. So you could even work it out and write down some constant, but as I said, this is far away from being optimal, but the important thing, it's a fixed constant, and in particular, it does not depend on the length of the interval. Okay, so this is this van der Corput lemma, and once you have this van der Corput lemma, we can now easily prove that we have the following dispersive decay for our equation. So if we compute the L1 to L infinity norm, so we assume that our initial condition is in L1, and we ask what is the infinity norm of the solution, then we get a 1 over t to the minus 1 over t to the 1/3 decay. Okay, so how do we get this?
Dimension 1, yeah?
This is dimension 1, yeah? And it's also quite interesting because in the continuous case you would expect a 1 over 2, but in the discrete case you get a 1 over 3. Okay, that's a specific thing of the discrete case, as we will see in the proof. Okay, so how do we prove this? As I said, first of all, we make this abbreviation here for V, and then we look at the corresponding integral. It's precisely of the form we had before, and the phase is given by this expression right here. Okay, so that's what you get when you just look at this integral and you have this phase here. Now, as I said, as before, we compute derivatives. We will find that both the first derivative can vanish, so we look at the second and we also look at the third derivative, and we get this here for the second derivative and this for the third derivative. So both of them have zeros, so I cannot apply just one case. So I need to split my interval, my domain of integration, into 4 intervals such that I have precisely 1 zero of either the second or the third derivative in this interval. And then just apply the van der Corput lemma on each of this interval. And as I said, as I need the third derivative, I get for those where I can apply it with the second derivative, I would get a 1 over square root, but for the other one, I get a 1 over the cube root. And since this is the worst case, I need to go for this, and I just get the 1 over square root of t decay. And the important thing, and also the reason why I did not look at the first derivative, is because the first derivative includes the v. Okay, and hence I do not get anything which is uniform in V, but this way I get something which is uniform in V. And by the way, this result is really best possible. Okay, it's not, apart from constants, of course, it's not possible to improve this result. And of course, it could also be proven by going to the literature, by maybe looking at this treatise by Watson on Bessel functions. There you will find that if the argument and the order of the Bessel function are both equal, and you look at the asymptotics, then it is minus 1 over 3. So you get precisely what we have seen in our theorem. So this is really best possible. And that means in our situation, if we look at V is equal to 2, then along this direction we have the slowest decay. But it really happens, so you cannot improve this, and you cannot do anything better. And the reason there is, as I again mentioned, at this point, both the first and the second derivative vanish, so neither the L is equal to 1 case nor the L is equal to 2 case of the van der Corput lemma would apply here. You need the L is equal to 3 case, and it's the best we can do. If you would exclude this ray here, so if you would exclude a small epsilon sector, then of course you can get better decay rates. You could get L is equal to 2, or you could even apply L is equal to 1 if you exclude certain rates. But if you want to have something which is uniform, then this is the best you can do. Okay.
Just a question. Can you also calculate a series in hours or adding hours of T?
Of course, you can write down a full asymptotic expansion if you want to, using this stationary phase method. But as I said, I want to have some estimates, and I want to have some uniform estimates, and this is the best estimate you can get in this situation. Precisely, because this is the leading, or yeah, it's the worst asymptotics you get in this direction, and I would like to be able to cover all directions. Because if I want to play these tricks I have shown you before, I cannot do it if I just know asymptotics in certain directions of the solution. I need something which applies to the entire solution, because I need to estimate the norm of the entire solution, and the entire solution is built up of these plane waves, so I need to control all of them and not just some of them. Unless, okay, if I make some assumptions that my initial conditions kind of leaves out certain parts, then maybe you can do better, but one doesn't want to do this. Okay, and moreover, one can do even better things if one uses these weights here, and one can prove in this weighted space here, as soon as this weight is larger than 2 over 3, you have T over 1 over square root, so 1 over square root of T decay, which is slightly better, but I think I'm not going to show you the proof of this one. This is really much more difficult to show.
And this is also in arbitrary dimension?
No, so far all I have said, this is just for this specific one-dimensional case. You can add a potential, that's okay, it's not going to destroy these estimates. Of course, for the free one, probably you can also get this quite easily by some properties of the Bessel functions. But for the general case with a potential, you can prove all these estimates using the same tricks and the same.
Higher dimensions, how would you go about it?
Higher dimensions is much different. So I should have mentioned what I have shown you so far really only works well in one dimension. Why? Because you have a good expression for your integral kernel. In the unperturbed case without potential, you still have, of course, you have the time evolution for the Schrödinger equation in arbitrary space dimensions, and you can explicitly estimate the kernel. But as soon as you add a potential, of course, you no longer have an expression, and then you need to apply different techniques, because you don't have an expression as an oscillatory integral for your kernel, so you can forget this. What you need to do is you would need this Born series approximation for the resolvent and then work for this. But these are purely abstract techniques, and of course there you will need more information on your potential to make things happen. So in a one-dimensional case, you can make this with very weak assumptions on it.
Multi-dimensional case, at least as an input for scattering theory, you only need it for free operators.
Yeah, sure, but then you need to do perturbation. And then you need to assumptions to make your perturbation series converge.
The estimate is similar for the continuous case also?
The powers here change. Okay? So in the continuous case, in d dimensions, you would get minus d over 2. Okay.
For the continuous case, the technique is more simple.
It's for the one-dimensional case, the technique is roughly the same.
The boundary point, there is not
singularity and something like that.
Okay, so I'll say something about this a little bit later on. In the one dimension, it's one thing, as you mentioned, this is correct. It depends on the behavior of the resolvent at zero. In order to understand this, in the one-dimensional case, you can understand this. In the multidimensional case, if you look into the papers, they're just assuming that there is no resonance, which means there is no singularity of the resolvent at zero, because there's no way of handling this in the multidimensional case. In the one-dimensional case, you can. And maybe if you're interested in these kind of things, I think it's a very nice proof, a very nice piece of analysis to show this. And actually, it took us quite some time. It was also a referee who said, because previously we had a weaker result for this case. And the referee said, hey, but it's easy to do this more general case. And then we said, okay, it's easy. Let's try it. But then we realized that the referee was wrong, and it's very difficult. But still, eventually, we got this, and it's a very cute proof. But still, I'm not going to say too much about this. Okay, and I think here I only have some special case here. Yeah. This is what is mentioned here. So I'm only going to show you the proof under this assumption here, which is the easy proof. It can be done under this assumption, but then things get much, much more tricky. Okay, so if you, as mentioned before, V is equal to 2 is the problematic direction where you have the 1 over square root of 1 over the cube root of t decay. And so somehow we only need to look at a sector containing this, because the remaining sectors are then easily covered. So we are going to split things, and we're going to distinguish two cases. So we look at the case where n minus k is smaller than t, and where it is larger than t. Okay? So in this region here, we of course have this, and we avoid this special ray. So this case is covered. We don't need to worry about this. So we need to look at the other case. Again, we split our domain of integration into these regions right here, where we know that the second derivative is larger than 1. And we split it into these regions right here, where we know that the first derivative is larger than this value right here. So you look at your trigonometric expression, and you just separate the zeros of the second and of the third derivative, and you make some explicit estimates using the trigonometric functions. Okay, so applying the van der Koppert lemma then on each of these intervals, you get the following expression right here. So if you take the sup when n minus k is absolute value is smaller than t, is given by this expression right here, which is precisely what we want. And now if we look at the other situation, then we have this estimate right here. Okay? But now we are going to use this additional information here. So we're going to split the 1 over 3 into a 1 over 2 and a 1 over 6. Okay? The 1 over 2 minus 1 over 2 is what we want. This is what we don't want. Okay, so we use this here and replace it by an n over k. And then this will be the weight function which shows up in our estimate. Okay? So in order to see this, right, we have our integral, our kernel, which just looks like this. And now if we estimate it like this, then we have this n minus k to the 1 over 6 here, and then the 1 over t to the minus 1/2 here. This is what we want, but if we just take the summation, then we have this n-dependent part here, and the sequence must just cancel this n-dependent part. Okay, that's precisely the assumption in this weighted space. Okay, so this is the simple trick to get this. And if you look, you see this would correspond then to sigma being larger than 2 over 3, and then everything works out nicely, and you have this result, like here. Okay, so let's, I don't think I'm going to do much at this point here. So let me just summarize again. So we looked at this one-dimensional case. We had this oscillatory integral. We had this van der Korput lemma, and we could use this van der Korput lemma in order to estimate the kernel and hence get the corresponding dispersive decay estimates for our solution. Now I want to look at the case where I add a potential to my unperturbed operator. And this is, of course, the situation where I can no longer write or where I can no longer solve this differential equation here explicitly. And as I said before, I have an expression in terms of Bessel functions, so I just could immediately estimate these Bessel functions using some well-known result. But in this case, this does no longer work on the one-hand side, but you still can write down at least an oscillatory integral. Even though not everything is explicit, at least the phase will be explicit, and you still can use the same approach as I'm going to point out in a moment. Okay, but for now, let me just, for simplicity, assume that this potential here is bounded. So this sequence Q is in L infinity. And again, existence of solution is just the exponential series and nothing else. So we have a nice group, uniformly bounded group of operators, and we don't have to worry about these things. We only need to worry about our dispersive estimate, about our decay estimate for the kernel. And problem is we can no longer solve these underlying difference equations. Okay, even though it's a very simple difference equations, it's this Jacobi equation here, but still it's not possible to write down a solution explicitly. So we need, first thing is we need a good formula for the time evolution and see what will replace our explicit formula, which we got from Fourier transform, which doesn't work anymore because Fourier transform would turn this into a convolution kernel, so we don't gain anything if we apply Fourier transform right here. So the first thing is we need to worry about a good formula for the time evolution, but I think I will stop at this point and not start this here because my time is almost over and I guess everybody's tired, so let's call it a day, at least from my point of view. Okay, thanks. Questions?
So the spaces is necessary for the estimate of this kernel.
The weight is necessary to get this better time decay here.
Yes, of course. Because the technical moments is the estimates of the kernel and the power 1/6.
Mm-hmm. Precisely. So I can take a little bit and shift it into spatial decay and hence get a better time decay.
The other weight is the negative, the other side.
Precisely. So the main thing is if you take these weights, you can get some better time decay out of this.
Can you estimate the solutions? I mean, where the solutions are in the free case? I mean, in the case of the Schrödinger equation.
So what?
In full space.
Yeah.
There are three. For example, you can say that the solution they follow more than the classical trajectory up to a dispersive.
I know what you allude to. I haven't thought about this in this discrete case, but I would say most likely you can do a similar thing. But I did not look at this, and I haven't seen it anywhere, but probably yes, because you have a very explicit expression for your time evolution, and you might be able to do the same trick and then write down some explicit long-time asymptotics for this in this case. Should be possible, but I haven't seen it and I haven't tried it.
For 2 and 3 dimensions, could it be also possible to fix it?
So in the unperturbed case, I don't know if there is a good expression for the time evolution. I mean, there should be, because you can do Fourier transform, but I mean, I don't think it has to be done, but it should be doable. If you add a perturbation, then things get more difficult. I mean, there are some abstract techniques developed by Kato and who was the... Yeah, there are a couple, there are many papers in this direction, but they all use more or less a very abstract approach. They use an abstract version of the van der Corput lemma, an operator-valued version of the van der Corput lemma, and they use some Born series as the perturbation series, but you need much more assumptions on your potential. But in principle, this approach can handle a large class of operators. So, and there it makes no difference how many dimensions you have, as long as you have some good expression for the free time evolution.
Which physical problems lead to such sort estimates for the discrete system?
As Hermann already mentioned in his talk, so there are two things. I mean, one is this tight binding approximation, which leads precisely to this kind of Schrödinger equation. Of course, what you should bear in mind, it's a simplified model, right? I mean, you cannot handle the realistic one, so you just do something simpler. It's the same thing with the nonlinear Schrödinger equation. You look at the discrete case because you have troubles with the continuous case, so you try to understand this simpler model first. And the main reason why I have chosen it for these lectures here is because I do not need to worry about all kind of technical problems. I want to focus on some of the main ideas. But as I said, this model is really used in physics via these tight binding approximations. So even physicists would consider this as an interesting model to study and to understand. And one should also mention that these Jacobi kind of operators, of course, also have a couple of other equations. So what is very much related, if you look at this Fermi-Pastor-Ulam problem, you are also in very similar situations, even though the linearization is not the Schrödinger equation here. And these things don't directly apply to FPU models. Yeah. You could also think of this, but it's these tight binding models in solid state physics. So it's a very simplistic model for a solid, a one-dimensional solid, a linear coupled chain of particles.
Just to be very broad in the question, but to get more or less a physical insight of what these bounds mean, or what exactly, as it were, is what's the practical application of?
So the practical application is really what I'm saying. You have decay of wave packages, right? I mean, you look at the solution of this equation here, and what this estimate tells you, you start with some sufficiently decaying solution, and then your solution will spread in time. So it will decay, the maximum of the solution will decay. And the physical reason, if you want, is because different plane waves travel at different speeds. So that means you understand the time evolutions of this problem. So that's the one hand, or the one side, and the other side would be really looking at these nonlinear perturbations of the equation where you have some solitary waves. So you look at some, again, plane wave solutions. You still can see you have a plane wave solution. And you also see from numerical experiments that these plane wave solutions are somehow stable, right? So you start close to such a solution. You stay close to a solution in a to be defined sense. And this is something you can prove using these techniques right here. And even more, we will see in the discrete case, again, proving existence of solution is not a problem. In the continuous case, even proving existence of such a nonlinear PDE is a problem. And there you already need this dispersive decays estimates in order to prove existence of solution. But we're going to have more on this in the following lectures, so I don't want to say more at this point.
There are also 5 diagonal matrices which are natural. The CMV comes to mind from Gerald Teschl. Now they're a little different because they model unitary operators. One expects something similar.
I don't know, if you look at the time evolution and your generator is a unitary operator, what does it tell you? I mean, is the time evolution, is it unitary or? It should not, because I mean, Stone's theorem is if and only if, right? So it will not be unitary. So, and of course it will not be, because if you, I mean, your spectrum is on the circle, right? So you at least generically you expect to have positive and negative real parts, so you expect that solutions will grow. So unless you make some spectral assumption that everything is on one side of the circle, which is probably not well motivated, I would say it's, I mean, you could do it, but I don't see much relevance there other than saying you do it because it can be done.
Because these models have the discrete analog for the, I mean, these are the
yeah, I know. I know what you're talking about, but I mean, nonlinear Schrödinger equation in some sense is part of this Ablovitzladik lattice. And the point is, what you need is the linearization of this equation, and the linearization is this thing here and not the CMV. I mean, it's the operator in the lax pair, but it's not the operator in the linearization. So it's a different thing. So the question would more or less be if you take the linearization of some equation in the Ablovitzladik lattice, can you prove dispersive estimates for this? Most likely yes, but yeah, but I can't tell you anything about this.
Question or comment? No? Okay, thank you.